All right, let's go to notes, shall we? How many of you are, yes? Number 4. Oh, sorry, it was 10. You're right, I just did the setup, it was 10. Okay. Anybody in APR? Nobody? Too bad. I love to see. These are so cool as somebody who can draw. But even if you can't draw, I am going to give you a little art lesson because drawing is important here. My brother is an art teacher, and he wants this done right, don't you know? Okay. So, here we go. I'm on the first part of the notes. When you do multivariate calculus, which I hope you do, typically Calc 3. When you do multivariate, you graph in 3 dimensions. Typically, in 3 dimensions, it looks like, depending on if you use the left-hand or right-hand graphing method, we go X here, Y here, and Z up. That's the left-hand graphing method. Some people use the right. What do you use in physics? Do you have any idea? What do we use in physics? Is this how you graph in 3 space for physics, or is this anything like this? Yeah. Okay. You have X. No, that's X. That's okay. So left hand and right hand is dependent on which hand. All right. Now, my point O is this. When you graph in 3 space, you no longer are looking at the XY plane like this. You're looking at it like this. When you look at it at a slant, it looks more like a parallelogram or at an angle, right? So first thing I want you to do is graph a little bit of a slanted Cartesian plane. Now, in graphing the square root function from 0 to 4, we're going to go 4x, and we'll only need to go 2 and y. Now, when you graph points here, for example, 1, 1, they need to be parallel to the x and y axis. So this would be 1, 1. And 4, 2 would be running parallel to the y-axis, parallel to the x-axis. Here's 4, 2. And therefore, if I graph the square root graph in 2-dimensional space, it might look, or in 3-dimensional space, it might look something like that. Now, the reason we're graphing like that now is because we're doing a totally different types of volume. Now, you've done volumes of revolution. That's one type of volume problem. It's the idea of taking a region and revolving it around an axis. And depending on what the region looks like, you could find the volume of that revolution in a lot of ways. But the idea is that in volumes of revolution, no matter what the region looks like, you always get kind of a bunch of circles because this stays the same distance all the way around. So circles are big in volumes of revolution. These will be different. Okay? Volumes of solids with known cross sections behave more like a 3D print. Have you ever? I know we don't have a 3D printer at this school, but it's terribly shaped. Imagine if you drop this, whatever, this rock or this vase or something in the 3D printer. The 3D printer is a lot like what we're doing today. The first thing is, hey, how are you? The first thing that the printer would do is, at the lowest height setting, it would go around the base and say, how far is it to that bottom level, and what's the shape of that? And then it makes a copy of that bottom level here. Then it would, the sensors of where it's at would go up about an inch, or depending on the setting. Then it would say, all right, this second part, second level? How far is it? And it would then add, or try and make an exact copy of that cross-section just above it. And then it would keep working up and up, gradually taking measurements of what does this cross-section, if I just took a slice, what does that slice look like? The thing is, though, it doesn't have to look like cylinders. It could look like anything. It could be a rock, like I said. It could be the grossest shape ever, and it would still just try to match all those cross sections. Now that is kind of like what we're doing here. Bear with me. And if we get to hand out passes, better. Okay, so the idea goes something like this. Usually we do this in geometric sense for calculus, all right? This might be the base of a solid. Think of it as a plot of ground off of which you will build your house. And the cross sections, don't worry about drawing this, they will all come out straight out from the base, and maybe each of the cross sections or each of the little slices are squares. And it might look something like, and it gets smaller and smaller, and it would look something like that, yeah? It could be the case that each of the cross sections are semicircles, in which case it would look more like a cornucopia kind of thing. Could be the case that those are triangles. And the cross section would look like that. We could find the volume of that. Could be the case that the slices don't even run this way. They run this way. In which case triangles would look more like that, going into the halves. Now those are all the different varieties of problems, or some of the different varieties of problems, and they all have their different calculus. That's where we're headed by introduction. Now let's talk about one that looks like this. Say if you had that same region, draw the region again, please. 4 and 2, 1, 1, 4, 2, looking like that. You draw it at an angle because we're about to show three-dimensional perspective. I understand if you feel like you're not that good at drawing, just try and draw what I'm drawing. If yours doesn't look just like mine, that's fine. Just do your best. All right? The picture will guide our calculus. Now, the cross sections are parallel to the y-axis. That goes to show how the slices run. Here's the y-axis, obviously. So if I go parallel to the y-axis, maybe I'll just do some slices at the whole numbers. Those are my slices, though actually I have infinitely many of them. Super paper thin. So far, so good? Now they're square. Now that is to say that I'm going to have, this is one side of the square, and the heights that are coming out of that are exactly the same way. So that might be the biggest square cross section. When I go to this one, surely this part isn't as long, so the heights coming out of those are not as long. And when I go down a little further, they're going to be a little less, and a little less. So all those cross sections are stacked up like a bunch of dominoes, and actually there's infinitely many in between. So if I connected all of the edges, all of those front corners, and all of those back corners, the figure might look something like that. Is that what yours looks like? All right. Now, the calculus. The question is to find the volume of that figure. It is the infinite sum of all the square prisms. So I need to basically find an infinite sum of many area of the base times heights. Now notice there's no pi r squared because it's not a revolution. I'm not revolving this, making a bunch of circular discs. There's no pi here. Okay? It's not a revolution, it's all squares. If you have pi in your work, then you don't know what you're doing. There's no problem. Okay? The area of the base. Now, the area of the base is going to be the area of that face. I'll come back to that. But the height is how thick the slices are. The height then is the thickness. And what do you reckon that will be? It'll be dx. Okay. Why isn't it dy? Well, I mean, imagine if I did a rectangle. Then wouldn't this width be a delta x? So taken super thin, isn't that a dx? The area of the base then, I'll find, but I'm going to be integrating with respect to x, because the thickness is the differential dx. Cool so far? The area of the base. The area of the base isn't the area of the base. Now this will be different each time based on the geometric shape. For this problem, it's a square. And so we know that the area of the base, when it's a square, is just whatever the side is squared. You follow? Oh, don't put x there, obviously, because it's not just whatever the x is. It's a little more complicated than that. Stop me if you have a question. This is definitely new and sometimes confusing, and I don't always explain things well. So if you have a question, jump in. Okay? So, the side. This side seems to vary. Sometimes it's longer, sometimes it's shorter, but it looks like the side is what? The curve, right? The side is the curve, which still has to be squared, dx. All right, so the curve then, because it's dx, needs to be the curve in x terms, so what am I going to integrate? Root x is the curve squared. So the volume of that incredibly complicated figure is nothing but the antiderivative for the definite integral of x dx. From where to where? 0 to 4. Surely then the antiderivative is a half x squared from 0 to 4. That's a half of 4 squared minus 0. And so the area, or the volume of that is 8. 8 cubic meters. Okay? So far so good? All right. Let's talk a little variations then. What if you had the same region but cross sections were parallel to the x-axis? Draw the region. Oh, okay. Don't pass out. All right. All right, now, parallel to the x-axis, draw the slices. Here's some slices. It doesn't really matter. You don't want your picture, you want your picture to look cool, but you don't want it to be too congested, all right? You don't want to confuse yourself. So aren't those slices parallel to the x-axis? And we're going to draw squares. Again, so you try and match the length of this with the height coming out and draw a square. Match the length, draw a square. Match the length, draw a square. Match the length, draw a square. If you were to connect the dots, which I do just because it looks cool, then these points all get connected, and these points all get connected. There's a fine line between it, just gets too cluttered. It doesn't look cool anymore. But all right, now then, if we look at one of these, the volume is the sum of many area of the base times the heights. We'll do the area of the base in the second, but what's the height now? The height is the thickness is here. Is that thickness dx or dy? Okay, the thickness goes like this. So imagine if the curve was a big old rectangle. Is this a change in x or a change in y? Is this delta x or delta y? That's delta y. I'm going up and down. I'm going up and down the y-axis, right? So the thickness is dy, and therefore the height is dy. Now, the side here is now going to be a little more complicated. It's tempting to say, oh, the side's the curve again. Not so much. Think right minus left. What's the right of it, each of these? Actually, let me go slower. The area of the base is still a square, yeah? So the area of the base is side squared. Cool? All right. But what is the side? Is it the curve? It isn't the curve because the curve would be the distance from an axis to the curve. Here's the curve. What's the side? Think right minus left. The right is 4. The left is the curve. So right minus left is 4 minus, now, square root of x or y squared? 4 minus y squared. Big right minus left. It's not always going to be straightforward in the curve like the past one. I wanted to start off easy, but sometimes things get a little wacky and you have to think, all right? Limits of integration, 0 to 4, 0 to 2. 0 to 2. And I put a pi in front, right? No, pi has nothing to do with it. I'm summing squares, volumes. There is no pi. All right. So, what is the antiderivative of 4 minus, actually, do you want to multiply it out, or should we throw it in our calculator? Throw it in the calculator. Go ahead, throw it in the calculator. Some of this is worth practicing putting in your calculator because it's no picnic. Some of these are pretty strange. You did?
Yeah,
Why did you almost die?
I choked on it.
I didn't even know this. So what we got there? 16 8/5, what, 48 fifths? What'd you get?
17.0.
No, that's not 48 fifths. What did I do wrong? Okay, 17 point.
0.66.
Okay. Is it a problem that that's different? The volume is not the same as what we just got. Is that right then? Did we make a mistake? Or are they totally different shapes? Different shapes, okay? This one, the height is totally tied to the x. The x is shorter. They're not going to be the same. They will be different. Don't expect them to be the same. All right? All right. Sometimes then getting slight variations here. Say you had f of x equals x. Now again, draw your axis at a slant. F of x equals x then would be right through here, y equals x. Negative x plus 4 is a y-intercept of 4 and a slope of down 1 over 1 until it hits an x of 4. Okay, we have two lines here. Here's F, here's G. Now the question is, do they want us to finish the area with the x-axis or the y-axis? They're saying finish it off with the y-axis, so I'm talking this region here, not the lower triangle. Be careful there, you identify the region correctly. You with me so far? All right. All right, now let's talk about the cross sections. There's two things to the cross section. Do they run parallel to the x or the y-axis, and what's the shape of those cross sections? In this case, they say parallel to the y-axis, so my slices will run parallel like that. And it says they're rectangular cross sections with height half the base. Well, if here's the base, then the height would have to be half that. And if this is the base, then half that might be a little smaller, and half of this would be really small. So it should come to a point, because as the base goes to 0, the height should go to 0, making it come to a point. A little slice of cheese. You with me? Alrighty then. So let's say then we get started. Volume is the sum of area of the base times the height. The area of the base, here's where I then start to do this, each part in one step. Please don't be in a rush to get to the calculus or the equations. Geometry first. By that I mean the area of the base is the area of a rectangle, the area of which is base times height. Okay? So use geometry first. Don't worry about the equations. You will confuse yourself if you try and go too fast. What's the height, dx or dy? The thickness is here. Is that dx or dy? Dx. So it's dx thick. If you went a bigger change, it would be, this is a delta x, and so on a small scale, that's a dx. Yeah? All right, now let's talk base. So obviously the limits of integration are a totally different problem. We'll get to that. Base of the rectangle. That's this distance. Each here that I'm doing in heavy red. What's the base? Or how will we find the base? Upper minus lower. Beautiful. I was hoping you'd say that. Thank you. Upper. What's the upper? G. G. Okay. G. And the lower? F. All right. That is base. What's the height? 1/2 the base. So if this is the base, then the height would be that same G minus F over 2. Right? Now keep in mind, I said height twice in this problem. There's really 2 heights going on here. There's height of the rectangle and then the height of the prism. Little h for height of the rectangle, capital H for height of the prism, which is a dx, right? All right. The only thing we need on top of that are the limits of integration. You could probably just guess and check it. What are they going to be? 0 to 2, yeah. Why not 0 to 4? That's y's region. Do you agree? The x region is from 0 to 2, and I agree. It doesn't make sense, right? In the interest of time, we'll bypass throwing that into the calculator, but that's the idea. You can imagine that maybe a more expedient way to put that in your calculator would be go to 1/2 of g minus f, the whole quantity squared, and just bring the half out front, right? All right, you try one, please. You try one. Let's see if we're making any headway, if there's at least a subset of you that are getting it. Yes, I do. Notice this time they're not even using the word parallel, they're using perpendicular. Let me know if you have any questions or comments. Oh, what about this? And usually most classes will say, you really pose this distance, two integrals, and most classes say that stuff like that. You guys just sound like a stuffer. So, two integrals. Do you see why it's two integrals?
No.
Okay, if you look at these rectangles, bases times heights, the base, here the base is right minus left, it's f minus 0, f minus 0, but hey, looky up here, now it's not f minus 0, it's g minus 0. So if you're doing with calculus, you'll actually have to do this with two integrals. Oops. All right. Second, what is the height, dx or dy? dy. I agree. For all cases, what's the height of every one of these rectangles? It is 2. All right, and then finally, for the first region or the lower region, what's the base? Right minus left, right minus left. What's the right? What's the left? The right is f. But it needs to be in y terms. So if y equals x is f, then instead of f, we're going to use just y. Because y and x are equal, right? In the next region, right minus left, right minus left. But this time the right is not f anymore, now it's g. Now if g was, negative x plus 4, then in y terms, if y or g is negative x plus 4, then in y terms wouldn't this be 4 minus y? So 4 minus y times 2 dy, and the limits of integration. The first region is from 0 to 2, and the next is from 2 to 4. All right, now, all that said, this is one of those cases where it actually would have been easier to do with geometry. If the height is always the same, then this is a case where it is a prism. By geometry, you could just do area of the base times the height. The area of the base is a triangle. The base of that triangle is 4. The height is 2. And the capital H height of the prism is 2. And so the volume of that thing is 8. All right? You follow? It's iffy, but we'll see. Okay, so let's go. Oh boy, we have so much to do, but we might have to finish these notes tomorrow. It's no worries. All right, take a look at this here graph. Would you try and sketch the region the best you can on your own? Okay. Parallel to the y-axis. All right. How we doing, people? Are we doing good? Or are we doing not so good? All right. All right, let's get rolling, shall we? So, we're going to add all those triangular cross sections to get the volume of the solid. It probably goes to a point at the edges, something like that. Yeah? Volume, as always, is the sum of all those little triangular slices. Lots of little triangular paper stacked together to make this 3D figure. There are three formulas for the area of a triangle. Do you know two of them? Base times height over 2. We're going to go for this option. That's one. Yes. What else? Come on. You should know the second one. The third one we know too. All right. The second one that you should know, because you learned it in pre-calculus, is 1/2 AB sine C. Yes, you did. You most definitely did. 1/2 AB sine C is the useful one here. The other one is Heron's formula, as I heard it. So when you know the three sides of a triangle, you can use what's called the semi-perimeter or half perimeter to find the area of a triangle. That's Heron's formula. But that said, this case, please don't use base height divided by 2. Your life will be harder. For equilateral triangle, it's so much easier. Here's why. Because if it's equilateral, what do you know about A and B? Please put your phone away before I slap you with it. Okay? What do you know about A and B? They're the same, right? And so that would be A squared. Also, what do you know about angle C? In an equilateral triangle, it must be 60 degrees. And so if you use 1/2 AB sine C, there's no guesswork. What's the base? What's the height? It's always the same. 1/2 A squared root 3 over 2 or root 3 over 4 A squared.
I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
That will always work.
Order just like Frankenstein. How about Miss Natalia as Alice in Wonderland's Queen of Hearts? Or Mr. Rickman as the cute little Pop-O-Matic maniac kitty? Mark your calendars for April 12th and 13th, next Friday and Saturday, for the annual improv show Melodrama. Cost is only $5 at the door, and the show starts at 6:30.
You should come. It'll be cool. What's the height here? DX or DY? Yes, yes. DX did.
Part of Devlin's only nationally competitive sports team and get the opportunity to cheer on North Carolina Jack.
All right. What about the side? A represents the side of the triangle.
Seventh and 12th grade students, you will not have
Is it
school
upper
on
minus
Tuesday,
lower
April
or
9th.
right
Seventh
minus
grade
left?
will be testing that day, but you will stay home. 8th, 9th, 10th,
Upper
and
minus
11th grade students, you
lower.
will have
What's the
state
upper?
testing, or you have state testing next Tuesday, which means you need to be here as usual at 7:30, but your day will be done
Do you
at
need
testing
lower?
at 12:20. The buses will pick up as usual, but will take you home at 12:20.
The only thing we need now is the intersection points.
Next week, we will say our CMAS testing schedule. Please look at the posters that will be posted in the hallway.
If you're interested in trying out for the Devlin High School pom team, 8th through 11th graders, please come pick up an information
Intersections
packet
are
in the main office today.
1 and -2.
Hey Jack, it's not too late to buy a yearbook. We only have 75 yearbooks left, so make sure to order one online before they're sold out. The price of the book will increase soon, so head to the yearbook tab on the website to get your yearbook before it's too late.
We're not going to get to that.
However, has a large number of fabulous pieces in a room.
You should be able to start the homework and probably set. I want you to get at least
Please come get it by Thursday.
half the homework done.
Please support the Devlin Boys Women Bag Tea Fundraiser
Actually,
on Wednesday, April 3rd.
preferably get a good
At the
chunk,
Qdoba located on
more than half.
30% of sales during this time will go back to the team, which is after membership.
Are you a female interested in learning more about a career in the law enforcement field? The Jackson County Sheriff's Office is looking for law enforcement career fair in
As far as I wanted to, I should have gone over the homework language.
Good recovery.
Thank you.